So I have here the formula that we used in the last couple of lectures, that we developed in the last couple of lectures, for modeling the value of a situation where the growth rate of a population was proportional to the size of the population. So remember, we started with this difference equation, right? And we derived this explicit formula for this situation. Now, we did this in the context of a savings account, right, where K was based on the interest. But you also see this used a lot, for example, to model the growth of populations. Right? It does kind of make sense to model the growth of a population this way, because the growth of a population is dependent on how many people are there, right? How many people, animals, whatever are there and are reproducing. The problem is we quickly run into trouble with this model. And the specific issue is that this model is unbounded. Right? As n gets big, there's no upper limit to how big the population can grow, and that's obviously unrealistic. Right? Physical space constraints, if nothing else, are going to limit how big it can get, and obviously there's all sorts of other considerations, access to resources and food and other things. So how can we fix this, right? How can we modify our model so that it gives us a result that's maybe a little more realistic? Okay, well, here's what I'm going to do. I'm going to assume that we have some idea, based on our understanding of the physical environment, what the maximum population size is. Right? So I'm going to let M equal the maximum population size. Now, what I need is I need a model that does two things, right? I'm going to look at the rate of change, right? How much it increases over this interval. And this needs to depend on two things. First, I want to have an a sub n term here, just like we did before, because that hasn't changed. As the size of the population increases, there are more people reproducing, the population is going to grow. Right? But I also need something that's going to slow it down. Right? So I also need something that's going to make this rate of change, this difference, smaller as the population increases. All right, so here's what I'm going to do. I'm going to add another term. I'm going to add a term m minus a sub n. All right, so I want you to think about what's happening here. As a sub n gets bigger, as a sub n gets close to n, this term is doing what I need it to do. It's getting smaller, right? And what happens when a sub n actually equals n, assuming that happens, right? If a sub n equals m, then this rate of change, this increase, is equal to m minus m times a sub n, and that is 0. Right? If once it hits that maximum, it can't grow any further. It has become 100% constrained by the environment, and that's good. That's what we want to see, right? We want to see the growth stopping at that point. And there is one other thing, so kind of the equivalent of this k, right? We'll put a constant out in front here that represents how fast the population reproduces. Right? That actually has a name. It's called the Malthusian parameter. It's named after the British philosopher Thomas Malthus, who did a lot of research, a lot of thinking into populations. Came up with some very depressing results about the relationship between population growth and food supplies, right? Which is why he gets the parameter here named after him. So I've got an example here for us to work with a little bit, right? And I've got a deer population that we've determined has a theoretical maximum of 400 animals. So that's the M in my previous equation, right? And its size after n years is modeled by this equation. Excuse me, this isn't the size. This is its growth, right? How much the population changes in a given year is modeled by this equation here. And this mirrors what we talked about on the last slide. This is the m minus a sub n part, and this is that Malthusian parameter. Now, finding an explicit solution isn't always practical. It's not something we're always going to be able to do. So sometimes what we will do instead is come up with what's called a numeric solution. And that means making a table, like the one I have over here to the right. So I've got an initial value here, right? I just kind of picked a number that's halfway to the maximum size. So we have something to work with. So what we're going to do to fill in this table is we're going to calculate delta A sub n, and then we're going to calculate the new population size, right? So how do I get these A sub n's? Well, these delta values are calculated using our formula here, right? So my formula says delta A sub 1 is equal, delta A sub 0 is equal to 0.001 times A sub 0, that's 200, times 400 minus 200. That comes out to 40. So how do we get A sub 1? Well, A sub 1 is A sub 0 plus delta A sub 0, which is 240, right? And then we do it again, right? Then we calculate delta A sub 1, that's 0.001 times 240 times 400 minus 240. Now you go to your calculator, and this is 38.4. That's the kind of result I wanted to see, right? The population got a little bigger, so the growth slowed down, right? It's not as much as it was before. So now I can get A sub 2, right? This is A sub 1 plus delta A sub 1, which is 278.4. All right, this quickly becomes very tedious, right? Trying to do this by hand, and this is where we really are living in a bit of a fortunate time. There are all sorts of software tools that you can use to do these calculations very quickly. You know formula once, and then you just copy and paste it down. I did this scenario here in Microsoft Excel and got these results. So you can see the change continues to drop off, 40 down to 38, down to 33, then 27, and so on. This rate dropped below 1 when I got to n equals 12, and it dropped below a half 2 generations later when I got to n equals 14. And at that point, you're adding less than the amount you would round each time. The population steadies off at 399. Eventually, if I had gone a few more iterations, I would have actually hit 400. Then we would have seen what we had, what I pointed out a couple slides back, where the deltas become 0, right? And the population will reach that steady state. So what you may have noticed on the last slide, there were some decimal values, right? And obviously decimal values don't make sense in this scenario. We're talking about deer. You can't have a fraction of a deer. So we do have to round, right? You could absolutely have legitimately rounded all of those values to integers. That would certainly have made sense. And that really kind of highlights a really important difference. We're doing this in the context of a discrete math class, right? So we expect to get discrete values. We expect to get integer values from our equations. There is, however, a strong relationship between these discrete difference equations, right? I have our difference equation version here, and this is the discrete case. So there is a strong relationship between discrete difference equations, and over here on the right hand side, this is the continuous equivalent. It's what's called a differential equation. Something if you've taken a first semester calculus class, you may have seen these briefly. This continuous version is an extremely powerful tool as well. In fact, if you really pursue your mathematics career, there are whole classes in differential equations offered at the university level, right? So we haven't really talked very much about continuous situations at all throughout this class, which is fine. It's not our focus, but it is good to know that there are connections back and forth between the continuous case that you already have learned so much about in algebra, trigonometry, maybe calculus classes, and these discrete cases that we're talking about here. So this actually brings us to the end of our discussion of sequences. In the next chapter, we're going to move on and talk about a completely new topic, something called a relation. We've already talked some about functions here. Functions are obviously very important in mathematics. When you first learn about functions, you very briefly see the definition of something called a relation, and then your professor or your teacher immediately says, okay, now if we add this extra requirement that every x value only gets mapped to exactly one y value, you get something called a function. Well, that's great because functions are super important and super useful, but so are relations. There's a lot to be said about what happens if we don't add on that requirement. So that's what we'll be talking about in the next chapter.